Okay, so we finally made it to the real numbers. The last few lectures have been building up the prerequisite knowledge that we needed to start formally studying the real numbers. And that's what we'll be doing. So this is now chapter 2, and this is the real numbers. Okay. In particular, right now, we are in section 2.1. And these are the properties of the real numbers. Okay, so I'm going to skip the very first section in this subsection, that deals with the algebraic properties of R. So these are things like the commutative property of addition, the existence of an additive inverse, the associative property of multiplication, these types of things that will be covered in more detail in a class like modern algebra. So in particular, the real numbers are said to be a field, and this is, we could go into that, but I think it's just going to waste time. We have a lot to cover in section 1. So please read 2.1.1, the algebraic properties of R. And again, this is just dealing with commutative properties, associative properties, identity elements, inverse elements, and things like this that we already pretty much know, right? So, excluding that, we should probably justify why the real numbers exist, right? Because we have quite a few systems of numbers, right? So we have like the naturals, we have the integers, and then we have the rationals, which are defined as the set of all A over B, such that A and B are integers, and B is non-zero. So these are a lot of numbers. These are three infinite sets of numbers. The naturals are a subset of the integers are a subset of the rationals. And you would think that, well, people thought for a long time that these are the only number systems that we needed. Until around the 6th century BC. So 6th century. Yeah, 6th century. C, Q is not enough. All, or maybe not all, is when this was discovered. And this is attributed to Euclid, but we can kind of find it on our own if we just consider a right triangle with sides 1 and 1. And then this side here would be 1 squared plus 1 squared. So this is going to be the square root of 2. So this square root of 2 number. This was the first number that was discovered that could not be accounted for by the rational numbers. Okay. So in particular, we need to prove this. So this is a theorem. There is no rational number x so that x squared is equal to 2. So there's no rational number x so that x squared is equal to 2. Okay. And we're going to walk through the proof of this. Once we prove this, then we have justification for numbers outside of the rationals, which we're going to call real numbers. And then once we have justification of existence, then we're going to derive various fundamental properties of the real numbers. So first, this proof. So this is a pretty famous proof, and it's going to be a proof by contradiction. So by way of contradiction, suppose x is some rational number with x squared equals to 2. Okay. So in particular, if x is in the set of rationals, and we know that it can be written as a ratio of a over b, where a and b are integers, and b is non-zero. So we can say thus there exists a and b, which are integers, with b non-zero, so that a over b all squared is equal to 2. Okay, that's just by the definition of x being a rational number. So if x is a rational number, it can be written as a over b, where a and b are integers, and b is non-zero. Moreover, we may assume that a over b is in its lowest form, lowest terms. In particular, we may assume that a and b share no common factors, since otherwise we could just like reduce and simplify the fraction. So moreover, we may assume a and b share no common factors. Since otherwise we could just reduce the ratio down further. So we just assume that it's already been reduced as far as we can. Okay, so then we can say hence so we have the square of a over b is equal to 2, so that implies a squared over b squared is equal to 2, which means that a squared is equal to 2 times b squared. Okay. Now we're going to need the notion of being an even number and an odd number, or an even number in particular. So just recall the definition that says that n is even whenever n is equal to 2 times k plus 1 for some integer k. Okay.
Hey, people are starting to have trouble reading it on the board. They're saying the letters are getting small.
Okay. Here?
That's fine, but you started getting smaller on the second board.
Oh, here. Oh, right around here, I can see that. Okay. So let me pull this forward a little bit. How about now? Is that a little bit better?
Yeah, that's a little bit better.
Okay. And again, speak up if you can't read anything.
Yeah, you were just getting smaller on the second board, and I think with cursive, it was giving people a little bit of a hard time.
Okay. Okay. I'll keep that in mind as we go forward. Oh, so here, thank you, by the way, for bringing that up. So here we have that a squared is equal to 2 times b.
Is that definition correct? I thought it was n equals 2k. I thought that's odd.
Get thrown out here. There. So b is an integer, so b squared is an integer. So a squared is equal to 2 times an integer, which means that it's even by definition. A squared is even. Okay. Now, if a squared is even, then it must be the case that a is even. So this implies a is even. Right? In the informal proof for that reason is that, so I'll maybe label this by star. So you would prove that by, so if you were to prove star, you should prove that n is odd implies n squared is odd. And that's not hard to prove. Okay, so that right there means that if a is even, then a, no, if a squared is even, then a is even. So I'll leave this for you to prove on your own. But that's the contrapositive of what I just wrote down. A squared is even, implying a is even. Okay. So by definition, there exists some number k, or some integer k, with a is equal to 2k. Right? So if a is even, then there is some integer k, so then a is equal to 2 times k. And I'll call this right here, I'll call this 1, that equation right there. So with equation 1, we have 2k squared, 2k all squared equals to 2b squared. And I just substitute 2k into this equation here. And that's true, then it must be the case that 4k squared is equal to 2 times b squared. Okay. And that, if and only if, we just divide by 2 on both sides of this equation, and then you get 2k squared is equal to b squared. Hence, b squared is even. Right? B squared is equal to twice times an integer, or 2 times an integer. This implies b is even. A contradiction. And why is that a contradiction?
Because they share no factors.
Right. So we assumed that we reduced A over B as far as we could, which means that A and B share no common factors. But then here, right, we have that A is even, so it has a factor of 2. And B is even, so it has a factor of 2, which means that they share a common factor, which is a contradiction because they don't share a common factor because we assume that we reduced that ratio. So many of you as math majors have seen this proof before. This isn't the best way that I would write it. I would spend a lot more time if I had more space, or if I could somehow maybe get like a fisheye for my camera so that you can see better. But this is the proof. But as math majors, you should probably know that this claim holds for, there's a more general theorem that this follows from. So the more general theorem states, so if x is a rational number, or no, so if p is a prime number, then there is no rational number x with x squared equals to p. That's the general theorem of this result here, because 2 is a prime number. So if this is true, then that implies this is true, right? And this is not too hard to define or to prove. The idea is the same idea. A over B is in A shares no common factors with B, so the greatest common divisor between A and B is 1, and then you get by a similar argument that A and B share a factor of P instead of 2. Okay? So, but I'll let you think about this. In fact, you should probably try to prove it. It's not hard, and I think a lot of you could prove it just following this similar pattern. But in particular, okay, this is what we're concerned with the first, and that just says that the square root of 2 is not a rational number. Or equivalently, no rational number squared is equal to 2. So we're missing numbers. And these numbers we're going to call real numbers. Okay. Okay, so now we have justification for this new number set. So with that justification, I'm going to now give you a series of properties that you're going to want to keep on hand in your notes for the duration of this section. Okay, so this is 2.1.5, and these are the order properties of R. Okay, so let me write this down. So there is a non-empty set P, which is a subset of R, that satisfies the following 3 properties. So part I. So A and B and P implies A plus B is in P. Part 2, A and B and P implies A times B is in P. And then part 3, so if A is a real number, then exactly one of the following conditions hold, the following property holds. Following holds. So we have A is in P, or A is equal to 0, or negative A is in P.
Professor, I think we lost your video feed.
Yeah, we lost.
Yeah, we lost you.
Yeah, see that, 1 second. Okay, it's trying to connect again. I wonder why that happened. Give me 1 second. So while that's trying to connect, I have a fix. Let me know if the screen comes on. I'm getting something for y'all. Almost there. Almost there. Almost there. Almost there. Okay, how does that look? Y'all can see?
Works for me.
All right, I'll just have to tilt the camera manually. Okay, so what is this set? So this set here is called the positive real numbers. So this set satisfies these properties. If A and B are in P, then the sum is in P. If A and B are in P, then the product is in P. And then if A is a real number, then exactly one of these properties holds. Okay, All right, so using this set here, we're going to build up quite a few other properties of the real numbers. Okay, so hopefully you can see that. All right. So with this this definition here of P, the positive real numbers, we're going to make a few notes. So if A is a positive real number, we write A greater than 0. If A is an element of P union 0, we write A greater than or equal to. Okay. If A, so if negative A is in P, we write A less than 0. And finally, if negative A is in P, union the set with 0, we write A is less than or equal to 0. And now, when you're less than or equal to 0, when you're greater than or equal to 0, you're said to be non-negative. If you're less than or equal to 0, you're said to be non-positive. In the strict case, you're just said to be positive or negative respectively. Okay. So next, we have a definition. So what does this definition say? So let A and B be real numbers. Okay. Let me try something real fast. Almost there. How well can you guys see from here?
Well enough.
I think
Is it better than the first time?
Oh yeah, it's definitely gotten better every time you moved it.
Okay, good. Okay, so, all right, here's our definition. So part A, if A minus B is in P, we write A greater than B or B less than A. That's just the notation that we're going to adopt. And then for part B, if A minus B is an element of P union 0, we write A greater than or equal to B, or B less than or equal to A. Okay. This is just a definition. Okay, now, oh, I almost forgot that this property 3 over here, I'm going to refer to as the trichotomy property. So this right here, property 3, is known as the trichotomy property. So this definition, together with the trichotomy property, states the following. Well, imply the following. So, it's important to note for all A and B and C that are real numbers. Wait, no, it's all A and B and the real numbers. Exactly one of the following holds. Namely, A is greater than B, or A is equal to B, or A is less than B. Okay. So exactly one of those properties will hold. Okay. And also, if A is greater than or equal to B, and B is greater than or equal to A, then A must equal to B. Okay. So let's prove some things now. So these are the fundamental properties for which we're going to build up the real number system. So we have the ordering properties for the positive real numbers. We have that every real number is either NP equal to 0 or negative of that real number is NP. So one of these holds for every number in R. We have this notion of greater than, equal to, based off of P. That's how we define it. And then we also define how to relate two numbers on the real number line by being in P according to this operation. So in particular, A is greater than B only when A minus B is in P. Okay. This together with this observation here, exactly one of these three holds, A greater than B, A is equal to B, or A is less than B. And then this observation here that if you're both greater than or equal to and less than or equal to, then you must be equal to. So now we're ready to finally build up the real numbers. Okay, so here's our first theorem. 2.1.7 theorem. Okay, so let A, B, and C be real numbers. So part A, if A is greater than B and B is greater than C, then A is greater than C. Now I know it might seem funny to you, this statement, but really we do need to justify why this is true based off of sort of what we consider our axioms. If we can consider this ordering property of the positive reals as this set of axioms, and with that we can build up the real number system and the various properties on that system. So we're going to have to prove that. Or B, if A is greater than B, then A plus C is greater than B plus C. And then part C, if A is greater than B and C is greater than 0, then C times A is greater than C times B. And if A is greater than B and C is less than 0, then C times A is less than C times B. So again, they seem kind of trivial, but we should prove them using the set axioms that I've defined, the set of axioms I've defined. So in particular, let's look at the proof of part A. Okay, so all we can work with is this information here, the little bit that I erased here, and these properties here. So in particular, I know that, so what am I going to do? I'm going to assume that and that, right? So assume A is greater than B, and B is greater than C. The part I just erased implies, so this implies that A minus B is a positive real number, and B minus C is also a positive real number. That was the part I erased before writing this theorem down. Remember? We say this whenever A minus B is in P. Okay? Then, if we have two numbers in P, then the sum of them is in P by 2.1.5 part I. So 2.1.5 part I implies that that plus that is in P. Which is equal to A minus C, that's in P. Make sure that you all can read that. Yeah. Because that's in P, these are positive real numbers. Part I over there implies that the sum of them is in P. And that sum just reduces to A minus C. So, A minus C is in P, then A is greater than C. So that proves part A of the theorem. If we assume that and that, by just using our ordering properties of R, we concluded that A is greater than C. So what about part B? So this is like a little sub-proof. Now we're going to get the proof of part B. So we're going to suppose A is greater than B. So let A be greater than B. Which implies A minus B is in B. Right? That's just the definition that we adopted for the inequality symbol. Okay. So what can we do now? So in particular, we can observe that, so we say, hence, the let's say, what did I write? Oh, you just add 0. Yeah. So A plus C minus C plus D is in P. Right? You see that? I just added a fancy version of 0. C and minus C, and then I factored out the minus from C and the B, so A plus C minus C plus D is in P. Now, if the difference is in P like that, then A plus C is greater than C plus B. And that is the proof of part B. All right, so now let's take the proof of part C. So there's like two subparts to this claim. So let's first assume A is greater than B and C is greater than 0. Let A be greater than B and C be greater than 0. I.e. A minus B is a positive real number. And C minus 0 is a positive real number. Okay. And we want to show that C times A is greater than C times B. Okay. So we make sure we got this going right. Well, we know that there's two things in P, just like part 2 over here, two things in P, then the product is in P. So by 2.1.5 double I, A minus B times C minus 0, that product has to be a positive real number because that's in P and that's in P. But this is just equal to, say, let me do it from the other side. It'll look nicer. C minus 0 times A minus B, which is equal to C times A minus C times B is in P. Because that's in there, and that's in there. Hence, C times A is greater than C times B by definition. So that's the first part here. For the second part, we assume that C is less than 0. So we're still in the proof of C. Part C. Maybe I can squeeze it in here, maybe. I might have to erase them. So now we have, if C is less than 0, that's this other case here. So A is still greater than B, but now we assume C is less than 0. Then negative C is a positive real number by the trichotomy property here, 2.1.5. If you're a real number, you're either a positive real number equal to 0 or negative of that number is in P. So if we assume that C is less than 0, then it's not in P, but negative C has to be. So now negative C is a positive real number, and A minus B is a positive real number. hence negative C times A minus B is a positive real number. And that's equal to negative C A plus CB. But then if you rearrange this, you get that CB minus CA is a positive real number, which implies this inequality right there. Okay. How much time? A little bit of time. Okay, so you can see that there was actual things to prove, even though these things seem simple, but again, we're assuming very little in the way of tools to use other than just these ordering properties and the definition of the greater than or less than symbol. Okay, so next theory. This is 2.1.8 theorem. Okay, so part A. So if A is in R and A is not equal to 0, then A squared is greater than 0. Part B, 1 is greater than 0. Okay. Now notice we haven't really introduced any numbers, right? Any like actual numerical numbers. So even though this seems obvious, it still needs to follow from our building blocks. And this next one might seem even more obvious. If n is a natural number, then n is greater than 0. Again, it might seem obvious, but we need to be able to prove it from our first principles. So proof of part A. Okay. So you can say let A be a real number with a non-zero. By the trichotomy property, since it's not 0, A is either in P or A is not in P. Okay. So if I had room, I would say by trichotomy, but I'm just going to say hence maybe, hence A is in P or negative A is in P. So we have two cases to consider. So if A is in P, then by 2.15 property 2, we can multiply A and A together, and that's in P. So A squared is in P, which implies A greater than 0. Or A squared greater than 0. If negative A is in P, the same thing holds. Then negative A times negative A is in P. Because, again, property 2. So then that proves part A. So now we need to prove that 1 is greater than 0. So proof part B. So since 1 is a real number with 1 not equal to 0, part A implies one equals to 1 squared is greater than 0. That's it. So after we've proven part A implies part B. Okay. So now part C. So if n is a natural number, then n is greater than 0. So we can prove this by induction and say, notice maybe I'll write it so that you might understand it a little bit better. So for our base case, this follows from part B. 1 is a natural number, so it's, and the natural numbers have ordering on them. So the first natural number is greater than 0. Now we need to show that it's greater than 0 for all natural numbers. So there's our inductive step. Okay. So for our inductive step, we need to assume our inductive hypothesis. So we assume if k is a natural number, then k is greater than 0. Okay. Now, in particular, we know that k is in P, right? So we just say next notice that if k is at some arbitrary natural number in P, and 1 is in P, again by part B, so 2.1.5 part I implies k plus 1 is in P. And so k plus 1 is greater than 0. And that finishes the proof of this theorem. So you can see how this is kind of annoying, honestly, having to recall previous things way over here, but we're building up the reals from like the bottom. And we're only assuming this, really. We're assuming this along with the algebraic properties of R that I didn't put on the board because there's too many to write out. But assuming algebraic properties together with this, we can build up all of the things from scratch that we need that will describe how inequalities work in the real, with the real numbers. Okay. All right, and we do have time to finish this up. Okay, so this is an important observation. Let A be a positive real number. Okay. And notice one half is a positive real number. By 2.1.5 part 2, the product of these two is also a positive number. So 2.1.5 part 2 implies that one half of A is a positive real number. So what does this mean about the positive real numbers? Like, can there exist a smallest positive real number? So go ahead and answer me. Can there be a smallest positive real number if this is always going to be true?
No.
No, there can't be a smallest, because suppose you have a smallest. So if A were the smallest, one half of A less than A is a contradiction. So with the real number system, the way that we're defining it, based off of these properties and the algebraic properties of the real numbers, there can be no smallest positive real number. You always find one smaller. So as a consequence of this, we get the following theorem, 2.1.9. And this theorem states that if A is a real number that satisfies zero less than or equal to A less than or equal to epsilon for all epsilon greater than 0, then A is equal to 0. So this theorem, this idea, this notion is telling us that even if it doesn't, like, it gives us a notion of equality when there isn't a smallest number, a smallest positive number. And hopefully, you really make note of this. This is like super, super important in analysis. This is the case. This gets used over and over and over again. Think back to Cal 1, Cal 2, or Cal 3. When you were defining limits on functions, you had these epsilons, and the epsilon could be as small as you want. Well, this is why. Because that's how we can get a notion of having equality under this strange number system. So let's look at the proof. It's kind of silly, honestly. So maybe suppose to the contrary. That A, so that 0 is less than or equal to A, which is less than epsilon, for all epsilon greater than 0, and A is not equal to 0. As opposed to the contrary if this is the case. So under this assumption, okay, so this implies, and A is a positive real number. So then since 1/2 is a positive real number, property 2152 for double I implies that epsilon naught equals to 1/2 times A is a positive real number. Thus, 0 less than epsilon naught, which is less than A contradiction, because A is supposed to be the smallest positive real number, so you shouldn't be able to squeeze anything below A and above 0. A contradiction. So, if you have this property that for any positive number epsilon, you're squeezed between epsilon and 0, even though there's not a smallest positive real number, you're equal to 0. So this is like something like 0.9999. That's equal to 1. It's like a consequence of this theorem. Okay. So you're following on that? You get the premise of what we've been doing. You assume algebraic properties. We take this as like a set of axioms, which we have definitions based off of those axioms. With that, we build up these fundamental properties of inequalities and equality. And once you have those fundamental properties built, then we can start exploring more and going into this very interesting and precise world of real analysis. It's like, just imagine it as in, I like to think of real analysis as kind of very closely related to like, you're building like a physical universe from scratch. So you're building up the little properties, and then once you have those properties, you can start exploring what you can do with those properties. And that's what we'll be doing for the rest of this month. So I'm going to go ahead and stop the recording here.